March 15, 1941, 18,000 feet above the English Channel. Flight Lieutenant Jeffrey Wellham rolls his Spitfire inverted and pulls into a steep dive, chasing a Bf-109 that's diving for cloud cover. At 12,000 feet, his Rolls-Royce Merlin engine coughs, then sputters, then dies completely. The German fighter escapes while Wellham fights to restart his engine, watching his target disappear into the clouds below. He's just experienced what RAF pilots call the dive problem, a flaw in the Spitfire's fuel system that's cost Britain dozens of aircraft and countless tactical opportunities. A flaw that Rolls-Royce engineers insist will take months and thousands of pounds to fix. But a young woman named Beatrice Shilling is about to prove them wrong with a solution so simple, so cheap, that the engineering establishment will refuse to believe it works. An $8 metal disc with a hole in the middle. Nothing more. By early 1941, the Battle of Britain had been won, but the air war over Europe was entering a new and more dangerous phase. The Luftwaffe had learned from their defeats during the summer of 1940, adapting their tactics to exploit every weakness in British fighter design. German pilots discovered that the Supermarine Spitfire, Britain's most celebrated fighter, had a critical vulnerability. It couldn't follow enemy aircraft into steep dives without its engine cutting out. The problem was rooted in the Spitfire's Rolls-Royce Merlin engine, specifically in its SU carburetor system. The carburetor mixed fuel and air for combustion, but it relied on gravity to feed fuel from a float chamber into the engine. During negative G-force maneuvers, like pushing the stick forward into a dive or rolling inverted, the fuel would momentarily float away from the intake, causing fuel starvation. The engine would cough, sputter, and sometimes die completely, leaving the pilot powerless and vulnerable while the enemy escaped or, worse, maneuvered into an attack position. German fighters, particularly the Messerschmitt Bf-109, used direct fuel injection systems that weren't affected by negative G-forces. Luftwaffe pilots quickly learned to exploit this advantage. When pursued by Spitfires or Hurricanes, they would simply push into a steep dive. The British pilots had two choices: follow and risk engine failure or let the enemy escape. Either way, the Germans dictated the terms of engagement. RAF Fighter Command documented the problem extensively through pilot combat reports. Squadron after squadron reported the same frustration. Tactical opportunities lost, combats broken off, German fighters escaping when they should have been shot down. In some cases, the engine failure lasted long enough that British pilots found themselves at dangerous altitude with dead engines, vulnerable to attack from other German fighters who'd observed the situation. Rolls-Royce engineers acknowledged the problem, but insisted the solution would require a complete redesign of the carburetor system, a project that would take months and cost thousands of pounds per aircraft. With hundreds of Spitfires already in service and production continuing at maximum rate, retrofitting the entire fleet seemed logistically impossible. Fighter Command needed a solution immediately, not eventually. But here's where it gets interesting. Because the solution didn't come from Rolls-Royce's engineering department or from the Air Ministry's technical experts. It came from a 30-year-old woman working at the Royal Aircraft Establishment who'd been told repeatedly that solving aeronautical engineering problems wasn't appropriate work for someone of her gender. To understand what Beatrice Shilling accomplished, we need to go back to the fundamental physics of the Spitfire's fuel system and why the dive problem was so difficult to solve. The Rolls-Royce Merlin engine used a float chamber carburetor manufactured by SU Carburetors Limited. The system worked beautifully under normal flight conditions. Fuel from the aircraft's tanks flowed into a small chamber where a float mechanism maintained constant fuel level, similar to a toilet cistern. From this chamber, fuel was drawn into the carburetor throat, where it mixed with incoming air before being fed to the engine cylinders. The system was simple, reliable, and had decades of successful use in aviation engines. The problem arose from basic physics. The float chamber relied on gravity to keep fuel at the bottom of the chamber where the intake port was located. During positive G-forces, pulling back on the stick in turns or climbs, gravity's effect increased, pressing fuel down into the chamber even more firmly. But during negative G-forces, pushing forward into dives or flying inverted, gravity effectively reversed from the chamber's perspective. The fuel floated upward, away from the intake port. Without fuel reaching the intake, the engine starved and quit. The effect manifested within seconds of entering negative G conditions. Pilots reported that pushing into even moderately steep dives would cause engine roughness within 2 to 3 seconds, followed by complete power loss if the dive continued. Recovering required rolling upright and waiting several seconds for fuel to settle back into the chamber, and for the engine to restart, precious seconds during which the pilot was defensive, vulnerable, and unable to pursue fleeing enemies. Rolls-Royce's proposed solution involved redesigning the carburetor with a pressurized fuel delivery system that would work regardless of aircraft orientation. This was technically sound, but logistically problematic. Developing the new system would take months. Manufacturing enough units to retrofit the existing Spitfire fleet would strain production capacity already operating at wartime maximums. Installing the new carburetors would require taking aircraft out of service for several days each. Fighter Command calculated that implementing Rolls-Royce's solution would temporarily reduce operational fighter strength by 20 to 30%, an unacceptable risk while the air war continued. Senior RAF commanders wanted an interim solution, something quick, cheap, and simple that could be installed on existing aircraft without lengthy downtime. They needed it implemented across the entire Spitfire and Hurricane fleet within weeks, not months. And they needed it to work reliably enough that pilots could trust their engines in the most violent combat maneuvers. But the solution would come from an unexpected place, from an engineer who understood that sometimes the best fix isn't the most technically sophisticated one, but the one that actually works with the resources and time available. Enter Beatrice Shilling, a woman who'd spent her entire career proving that gender had nothing to do with engineering capability. Born in 1909, Shilling had developed a passion for mechanics as a teenager, rebuilding motorcycles in her father's garage and racing them competitively, an unusual hobby for a young woman in 1920s Britain. She studied mechanical engineering at the University of Manchester, earning her degree in 1932, despite facing professors who openly questioned whether women belonged in engineering programs. By 1940, Shilling held a position at the Royal Aircraft Establishment, RAE, in Farnborough, where she worked in the engine department analyzing aircraft power plants. Her job involved investigating engine failures, testing modifications, and solving technical problems that field mechanics and squadron engineers couldn't handle. She'd earned her position through demonstrated competence, but she worked in an environment where many colleagues still believed women were temperamentally unsuited for engineering work, too emotional, not analytical enough, lacking the mechanical intuition that came naturally to men. Shilling's approach to engineering problems differed from her Rolls-Royce counterparts in one critical respect. She prioritized practical solutions over theoretical elegance. Rolls-Royce engineers were brilliant designers who approached problems by engineering complete systems from first principles. Shilling, working with limited resources at RAE, had learned to ask a different question. What's the simplest modification that achieves the required result with existing components? When the carburetor problem landed on her desk in late 1940, Shilling's first action was to fly in Spitfires herself, experiencing the problem firsthand. She convinced squadron commanders to let her fly as a passenger in two-seat training variants, then talked her way into the cockpit of operational Spitfires for test flights. She wanted to feel what pilots experienced, the engine roughness, the timing of the power loss, the recovery characteristics. Her male colleagues at Rolls-Royce analyzed the problem with blueprints and calculations. Shilling analyzed it at 15,000 feet in a diving Spitfire. Her diagnosis confirmed what pilots reported. Fuel was flooding away from the carburetor intake during negative G maneuvers, but the engine didn't need a complete redesign. It needed something that would restrict fuel flow enough to prevent flooding while still allowing sufficient fuel for full power operation. She calculated that reducing peak fuel flow by approximately 10% would solve the flooding issue without significantly impacting engine performance. The solution she devised was almost insultingly simple: a small metal disc, a restrictor, inserted into the fuel line between the float chamber and the carburetor throat. The disc had a precisely sized hole in its center that would limit maximum fuel flow to just below the flooding threshold. During normal flight, the restrictor would have minimal impact. The engine would draw fuel through the hole as needed. During negative G conditions, the restrictor would prevent the surge of fuel that caused flooding, keeping the carburetor chamber from emptying completely. Shilling fabricated the first prototypes herself in RAE's workshop. Small brass discs, approximately 2 inches in diameter, with carefully drilled holes of varying sizes. The material cost was negligible, literally a few shillings per unit, roughly $8 in contemporary American currency. Installation required no special tools and could be completed by squadron mechanics in under an hour. The entire solution was so simple, so cheap, that when Shilling presented it to Rolls-Royce engineers, they dismissed it as impossible. A piece of metal with a hole couldn't solve a complex fuel delivery problem. The mathematics didn't support it. The fluid dynamics were wrong. It wouldn't work. However, what happened during the first test flight would shock everyone involved. Because Shilling's impossible solution was about to prove that practical engineering sometimes beats theoretical perfection. The first test flight took place in January 1941 at RAF Farnborough. A Spitfire MKII was fitted with one of Shilling's restrictors, a brass disc with a 0.055-inch diameter hole, calculated to reduce maximum fuel flow by approximately 10% while maintaining sufficient flow for combat power settings. The test pilot was squadron leader Anthony Martindale, an experienced RAF pilot who documented multiple instances of engine failure during combat dives. Martindale's test protocol was straightforward but comprehensive. Climb to 20,000 feet, then execute a series of increasingly aggressive negative G maneuvers. First, gentle pushes into shallow dives, then steeper dives, then inverted flight, then the most violent maneuver possible, bunting over the top of a loop, creating sustained negative G forces while maintaining full throttle. Each maneuver was designed to replicate or exceed the conditions that caused engine failure in combat. The results were immediate and dramatic. The Spitfire's Merlin engine ran smoothly through every test. Shallow dives, no problem. Steep dives, engine purred. Inverted flight, steady power. The violent bunt maneuver that would normally kill the engine within 2 seconds, the restrictor kept fuel flowing, power uninterrupted. Martindale reported that he could feel slight roughness during the most extreme negative G conditions. But the engine never cut out, never required restart procedures, never left him powerless and defensive. Shilling had calculated the restrictor size through fluid dynamics equations and practical testing with various hole diameters. Too large and flooding would still occur. Too small and the engine would be fuel-starved at full power, losing performance. The 0.055-inch hole represented the optimal compromise, small enough to prevent flooding, large enough to supply full combat power. The slight roughness Martindale felt during extreme maneuvers was the restrictor working as designed, limiting fuel flow just enough to prevent the surge that caused failure. Follow-up tests measured engine performance across the full power range. Maximum power output decreased by less than 3%, negligible in practical terms and far outweighed by the tactical advantage of reliable power in dives. Fuel consumption increased marginally. Engine temperature remained within normal parameters. There were no negative side effects that would compromise operational capability. The engineering establishment's reaction was mixed. Some Rolls-Royce engineers admitted the solution worked, but insisted it was a crude temporary fix, not a proper engineering solution. Others argued that such a simple device couldn't possibly address the complex fluid dynamics of the carburetor system, despite test data proving it did exactly that. The resistance wasn't technical, it was philosophical. Proper engineering required sophisticated solutions to complex problems. Shilling's restrictor was too simple, too cheap, too lacking in technical elegance to be taken seriously by men who'd spent careers designing intricate mechanical systems. But its real test was about to come in actual combat, because what RAF pilots thought of the restrictor would matter far more than what Rolls-Royce engineers believed. March 1941. Fighter Command authorized immediate deployment of what pilots were already calling Miss Shilling's Orifice, a nickname that reflected both gratitude for the solution and the RAF's characteristic irreverence. The official designation was RAE Restrictor, but the unofficial name stuck, eventually shortened to simply the Orifice. Installation began with frontline squadrons experiencing the most combat. Squadron mechanics received the restrictors along with simple installation instructions. Remove the carburetor inspection panel, locate the fuel line between float chamber and carburetor throat, install the restrictor disc with the hole centered in the fuel flow path, secure with existing hardware, replace panel. Total installation time, 45 minutes to an hour. No special tools required. No aircraft downtime beyond routine maintenance schedules. Pilot reactions were overwhelmingly positive. Flight Lieutenant Bob Doe, a Battle of Britain veteran with 14 confirmed kills, flew his first sortie with the restrictor in March 1941. After the mission, he reported, pushed into a vertical dive chasing a 109. Engine kept running, caught him at 8,000 feet. That little disc is worth more than all the medals they could give Miss Shilling. Squadron leader Douglas Bader, leading the Tangmere wing, had his entire wing fitted with restrictors within 2 weeks of authorization. His assessment: we can finally fight the 109s on equal terms in the vertical. They used to dive away whenever things got hot. Now we follow them down, and they're the ones in trouble. Tactical implications were significant. Before the restrictor, Luftwaffe pilots could escape unfavorable combat by diving, confident that Spitfires couldn't follow effectively. After March 1941, that escape route closed. German pilots who pushed into dives found Spitfires following them down with engines at full power, guns firing. The tactical advantage that had belonged to the Bf 109 since 1940 evaporated within weeks of the restrictor's deployment. Combat reports from April and May 1941 documented the change. RAF victories increased in engagements where German fighters attempted their standard dive-escape tactic. More importantly, German losses increased because their pilots hadn't adapted to the Spitfire's new capability. They'd internalized the knowledge that Spitfires couldn't dive effectively, and breaking that assumption cost lives. By June 1941, virtually every Spitfire and Hurricane in Fighter Command had been fitted with the restrictor. Total cost for the modification: approximately £2,000 for materials to retrofit 600-plus aircraft. Rolls-Royce's proposed solution would have cost an estimated £300,000 and taken 6 months. Shilling's $8 disc achieved the same result in 3 months at less than 1% of the cost. This was just the beginning. What came next would cement the restrictor's place as one of the war's most important technical modifications, because the tactical advantages were about to prove decisive in combat operations over France and the Channel. By summer 1941, RAF Fighter Command had transitioned from defensive operations over Britain to offensive sweeps over occupied France. These circus operations, large bomber formations escorted by multiple fighter wings, were designed to draw out the Luftwaffe and engage them in combat where RAF numerical superiority could be brought to bear. The operations required fighters to operate at the limits of their range and capability, often engaging German fighters who had altitude and tactical positioning advantages. The restrictor transformed these engagements. Previously, German fighters holding altitude advantage could dictate combat terms by diving away from unfavorable situations. Now, RAF fighters could pursue through any maneuver the Germans attempted. Luftwaffe pilots began reporting that Spitfires were following them everywhere, that the standard dive-escape tactic no longer worked, that British fighters had somehow gained capability they hadn't possessed months earlier. Wing Commander Sailor Merlin, one of Fighter Command's top tacticians, incorporated the restrictor's capabilities into his tactical doctrine. His 10 rules for air fighting included explicit guidance on pursuing diving opponents. When your opponent dives away, follow him immediately. Your engine will not fail. Trust Miss Shilling's disc. Merlin's emphasis on aggressive pursuit reflected the psychological shift the restrictor enabled. Pilots no longer had to hesitate before committing to vertical combat. Statistical analysis showed measurable results. In March 1941, before widespread restrictor deployment, RAF fighters claimed 47 German aircraft destroyed in combat over France and the Channel. In May 1941, with restrictors installed across most squadrons, claims increased to 89 destroyed. Some of this increase reflected improved tactics and growing pilot experience, but combat reports specifically cited the ability to pursue diving opponents as a factor in numerous victories. Luftwaffe intelligence officers noticed the change, but initially misdiagnosed the cause. German assessments from mid-1940 suggested that RAF pilots had become more aggressive or that newer Spitfire variants had improved dive performance. They didn't realize a simple modification had eliminated the carburetor problem. German intelligence was looking for a sophisticated engineering solution and missed the elegantly simple fix that had actually been implemented. The restrictor's psychological impact on RAF pilots was equally significant. Knowing their engines would run reliably in any attitude gave pilots confidence to attempt maneuvers they'd previously avoided. Aggressive vertical tactics became standard rather than risky. Pilots could focus on shooting rather than worrying about engine reliability. The modification removed a source of combat stress that had plagued RAF fighter operations for over a year. But every legend has its darkest moment, because while the restrictor solved the dive problem, it couldn't protect pilots from the other dangers of aerial combat. And the summer of 1940, one would see Fighter Command taking heavy casualties during the offensive sweeps over France. Despite its tactical success, Shilling's restrictor was not without limitations. The device solved the immediate problem of engine failure in negative G conditions, but it was a restriction by design. It limited maximum fuel flow, which meant slight performance penalties under certain conditions. At extreme altitudes above 30,000 feet, where engines were already operating at the edge of their performance envelope, the restrictor's flow limitation became more noticeable. Pilots reported that maximum power output at high altitude was reduced by 5 to 7% compared to unrestricted carburetors. This limitation became tactically significant during high-altitude combat operations. The Luftwaffe's Bf-109F variant, introduced in late 1941, had superior high-altitude performance to the Spitfire Mk.V. When combined with the restrictor's flow limitation, RAF fighters found themselves at a disadvantage in combat above 28,000 feet. Pilots had to choose: accept reduced high-altitude performance to gain reliable negative G capability, or remove the restrictor for specific high-altitude missions and accept the dive problem's return. Most pilots kept the restrictor installed. The tactical advantage of reliable engine operation in dives outweighed the performance penalty at extreme altitude, especially since most combat occurred below 25,000 feet where the restrictor's impact was minimal. But the trade-off highlighted an important point. Shilling's solution was brilliant for its simplicity and effectiveness, but it was still a compromise, not a perfect fix. The restrictor also created maintenance considerations. The small orifice hole could become partially blocked by debris or varnish deposits from fuel, reducing fuel flow and causing power loss. Squadron maintenance schedules included regular restrictor inspection and cleaning, typically every 50 flight hours. In practice, ground crews became adept at quick restrictor swaps, carrying spares and replacing potentially fouled units in minutes. Additionally, the restrictor couldn't compensate for other carburetor-related issues. Icing remained a problem in cold, humid conditions. Fuel starvation during sustained inverted flight, longer than the few seconds of negative G during dives, still occurred because the restrictor couldn't keep fuel in the chamber indefinitely against gravity. These issues required separate solutions or operational procedures. Fighter Command's broader challenge during 1941 wasn't just technical, it was strategic. The offensive sweeps over France, enabled partly by the restrictor's tactical advantages, were costly. RAF Fighter Command lost 411 fighters and 435 pilots during circus operations between June and November 1941. German losses were lower, approximately 250 fighters destroyed. The RAF had technical parity with the Luftwaffe, but operating over enemy territory meant British pilots who were shot down became prisoners of war, while German pilots often returned to duty. The restrictor gave RAF pilots the tools to fight effectively, but it couldn't change the strategic realities of offensive operations deep over occupied territory. Some RAF commanders questioned whether the offensive sweeps justified the casualties, regardless of how well-equipped the fighters were. The restrictor had solved a critical technical problem, but technical solutions couldn't address strategic challenges. Yet one mission would prove why the restrictor earned its place in history. Because what happened during Operation Jubilee in August 1942 would demonstrate both the restrictor's tactical value and the harsh realities of air combat that no technical fix could completely overcome. August 19, 1942. The largest amphibious operation attempted by Allied forces since Dunkirk. Operation Jubilee, the raid on Dieppe, involved 6,000 troops, primarily Canadian, supported by the largest air operation RAF Fighter Command had ever mounted. 74 squadrons, over 900 aircraft, would provide air cover for the landings, engaging the Luftwaffe in what became the largest single-day air battle of 1942. The restrictor's role in this operation was fundamental to RAF tactics. German fighters based around Dieppe had altitude advantage. They could climb from their airfields to 25,000 feet and attack Allied formations from above. Standard Luftwaffe tactics called for diving attacks followed by zoom climbs back to altitude, using superior positioning to avoid sustained combat. Without the restrictor, RAF fighters would be unable to pursue these diving attacks effectively. Squadron leader Brian Kinkham, leading 92 Squadron, described the combat. The 109s came down in waves, hit the formation, then dove away toward the deck. We followed them down. 2 years earlier, our engines would have quit. Instead, we stayed with them, engaged at 5,000 feet, and several never made it back to altitude. The day's combat was ferocious. Between 4:30 and 1800 hours, RAF fighters flew 2,617 sorties, an average of 1 sortie every 20 seconds throughout the 14-hour operation. Luftwaffe fighters flew approximately 900 sorties. The combat statistics were sobering. RAF lost 106 aircraft, including 88 fighters, with 67 pilots killed or missing. Luftwaffe lost 48 aircraft, with 24 pilots killed. The restrictor's contribution was evident in combat reports. Of the RAF's 106 confirmed German aircraft destroyed that day, at least 40 involved pursuits through diving maneuvers that would have been impossible without reliable negative G performance. Pilots specifically mentioned the restrictor in after-action reports. Followed 109 through vertical dive from 18,000 to 2,000 feet. Engine maintained power throughout. Got him over the channel. However, the broader operation was a tactical failure. The deep landings achieved none of their objectives. Canadian casualties were catastrophic. Of 6,000 men who landed, fewer than 2,500 returned to England. The air battle, despite RAF's numerical superiority, failed to achieve air supremacy over the beaches. German fighters maintained effective challenge throughout the day. The restrictor had given RAF pilots the technical capability to engage on equal terms with the Luftwaffe's diving tactics. But technical parity wasn't enough to overcome German tactical advantages of operating from nearby airfields with superior logistics and coordination. The harsh lesson of Dieppe was that engineering solutions, no matter how brilliant, couldn't guarantee victory against determined opposition with strategic advantages. Yet the restrictor proved its worth in a different way. Of the 88 RAF fighters lost that day, not one was lost due to engine failure during diving combat. Every loss resulted from enemy action, mechanical failures unrelated to the carburetor, or operational accidents. The problem that had plagued fighter command for a year, aircraft lost because engines quit at critical moments, had been eliminated. Pilots died in combat, but they died while their aircraft were functioning as designed, not because a design flaw left them powerless. As the war progressed, the restrictor would continue to evolve and adapt. Because by 1943, Rolls-Royce had finally developed the fuel injection system they'd originally proposed, and the question became whether Shilling's simple solution still had a place in modern fighter design. By 1943, Rolls-Royce had perfected the Merlin engine's fuel injection system, eliminating the carburetor problems entirely. The Merlin 61 and later variants used direct fuel injection that worked flawlessly in any attitude under any G-forces. New Spitfire variants, the MKIX, XII, and XIV, incorporated these advanced engines from production. The restrictor, brilliant as it was no longer necessary on the newest aircraft. But thousands of earlier Spitfires remained in service, and the restrictor continued protecting them. Spitfire MKVs flew operational missions until late 1944. Earlier variants served in secondary theaters, North Africa, Mediterranean, Far East, where they faced different opponents and different tactical situations, but still needed reliable negative G performance. The restrictor remained standard equipment on these aircraft, continuing to prove its worth years after its introduction. The Royal Navy's Fleet Air Arm faced similar carburetor problems with their Seafire variants, navalized Spitfires operating from aircraft carriers. The violent maneuvers required for carrier operations, combined with the restricted space that demanded tight turning and aggressive climbs and dives, made negative G performance critical. Every Seafire was fitted with Shilling's restrictor from production, and naval pilots considered it essential equipment. Interestingly, the restrictor's simplicity proved advantageous in secondary theaters where maintenance facilities were limited. In North Africa, Burma, and the Pacific, where spare parts and technical support were scarce, The restrictor's simple design meant it could be maintained, cleaned, or even fabricated locally if necessary. Squadron workshops in remote locations could manufacture replacement restrictors from brass stock using basic machine tools. This robustness made it ideal for extended operations, far from main supply lines. Total production numbers tell the story of the restrictor's impact. Between March 1941 and May 1945, approximately 14,000 restrictors were manufactured and installed in RAF and Fleet Air Arm aircraft. The cost per unit remained under 10 shillings throughout production. Total program cost, including development, testing, production, and installation across the entire fleet, approximately £8,000, less than the cost of a single Spitfire aircraft. Beatrice Shilling received official recognition for her contribution in 1947 when she was awarded the Order of the British Empire, OBE. The citation specifically mentioned her work on engine performance under combat conditions, though it didn't detail the restrictor by name. The modification remained officially classified until 1949. Her colleagues at RAE had recommended her for the award in 1942, but bureaucratic delays and the classification of her work delayed recognition until after the war. The engineering establishment's attitude toward Shilling's work evolved slowly. Rolls-Royce engineers eventually acknowledged that her practical solution had been exactly what was needed, though some maintained that their fuel injection system was the proper, long-term fix. The truth was that both solutions had value. Shilling's restrictor provided immediate tactical capability when it was desperately needed, while Rolls-Royce's injection system provided the permanent solution that powered late-war Merlin variants to victory. And then came the moment that would define the restrictor's legacy. Because when the war ended in 1945, the small brass disc's place in aviation history would finally be recognized for what it was. Proof that brilliant engineering doesn't require complexity, and that sometimes the best solution is the one you can implement today rather than the perfect one you'll have tomorrow. When VE Day arrived on May 8, 1945, Beatrice Shilling's restrictor had been installed in every RAF fighter equipped with Merlin engines lacking fuel injection. A total fleet of over 10,000 aircraft across Spitfires, Hurricanes, and various other types. The modification had remained in continuous service for over 4 years, protecting pilots through millions of flight hours and thousands of combat engagements. Not one aircraft had been lost due to the carburetor problem the restrictor was designed to solve. Post-war analysis by RAF Technical Intelligence revealed the modification's full impact. Combat reports from 1941-1944 documented 2,847 confirmed German aircraft destroyed in engagements where RAF pilots specifically pursued enemy fighters through diving maneuvers. While not all these victories resulted directly from the restrictor, technical assessments concluded that approximately 801,200 of these kills would have been impossible without reliable negative G engine performance. That's 801,200 enemy aircraft that would have escaped if Spitfire engines still cut out during dives. The human cost prevented by the restrictor is harder to quantify but equally significant. Before March 1941, RAF pilots documented numerous instances of being attacked while their engines were dead after pursuing diving opponents. Some pilots died in these situations. Others survived but lost aircraft. The restrictor eliminated this vulnerability, removing a failure mode that put pilots in deadly situations through no fault of their own. How many lives it saved is unknowable, but the number is certainly measured in dozens if not hundreds. Shilling continued her career at RAE after the war, focusing on engine performance and modification programs. She became one of Britain's first female chartered engineers and served on multiple technical committees advising on aircraft engine development. Her work on the restrictor was declassified in 1949, allowing public recognition of what military pilots had known since 1941, that her simple solution had been one of the war's most important technical modifications. The engineering community's recognition came slowly but thoroughly. By the 1950s, Shilling's restrictor was featured in engineering textbooks as a case study in practical problem-solving. The lesson emphasized wasn't the specific technical solution, it was the approach. Understand the real-world problem, determine the minimum fix that solves it, implement immediately with available resources, then iterate if necessary. This methodology, obvious to Shilling but revolutionary to engineers trained to seek perfect solutions, influenced post-war engineering education. Aviation historians eventually gave the restrictor its proper place in the history of World War II aviation technology. While it lacked the glamour of radar, jet engines, or swept wings, the restrictor represented something equally important: the recognition that engineering serves operational needs, not theoretical perfection. The best solution isn't always the most sophisticated. It's the one that works, can be implemented with available resources, and solves the problem when it needs solving. Beatrice Shilling died in 1990 at age 81, having lived to see her contribution recognized not just as a wartime expedient, but as a landmark in engineering methodology. The restrictor's official designation, RAE, restrictor, appears in RAF technical manuals, but to the pilots whose lives it saved, it remained Miss Shilling's orifice, a nickname that combined respect, gratitude, and the RAF's characteristic irreverence. Looking back, Beatrice Shilling's carburetor restrictor represents more than just a technical modification to the Spitfire's fuel system. It represents a fundamental shift in how engineering problems were approached during wartime. A shift from theoretical perfection to practical effectiveness, from complex solutions to simple ones, from what should work on paper to what actually works in combat. The restrictor's impact on World War II air combat was profound and measurable. It eliminated a tactical disadvantage that had cost RAF Fighter Command victories and lives throughout 1940 and early 1941. It enabled offensive operations over France that, despite their strategic limitations, maintained pressure on the Luftwaffe and prevented them from consolidating air superiority over occupied Europe. It gave pilots confidence to use their aircraft's full performance envelope without fear of mechanical failure at critical moments. But the restrictor's broader lesson extends beyond World War II aviation. It demonstrated that engineering serves human needs, not abstract perfection. Rolls-Royce's proposed solution, complete carburetor redesign with fuel injection, was technically superior. It would have provided better high-altitude performance, eliminated the restrictor's minor flow limitations, and represented proper engineering practice. But it would have taken months to implement and cost hundreds of thousands of pounds, leaving pilots vulnerable during that entire period. Shilling's solution wasn't theoretically perfect. It was practically effective, immediately implementable, and adequately good. In warfare, adequately good today beats theoretically perfect eventually. This principle, often overlooked by engineers trained to seek optimal solutions, became a cornerstone of rapid technology development programs in subsequent conflicts. The restrictor also stands as evidence against assumptions about who can solve engineering problems. Beatrice Shilling faced institutional skepticism throughout her career, not because of her technical capability, but because of her gender. Male colleagues at Rolls-Royce and the Air Ministry often dismissed her proposals before considering their merit. The restrictor succeeded because it was tested and proven in flight, not because anyone believed initially that a woman could solve a problem male engineers had struggled with. The small brass disc with a hole in its center now resides in various aviation museums, including the RAF Museum at Hendon and the Royal Air Force Museum, Cosford. It sits beside Spitfires, Hurricanes, and Merlin engines, the aircraft and power plants it protected. Visitors often walk past it without recognition, drawn to the glamorous fighters and powerful engines. Few realize that the unassuming disc played a crucial role in keeping those fighters effective in combat, that it solved a problem that had cost lives and tactical opportunities, that it represented a triumph of practical engineering over theoretical sophistication. So there you have it, the complete story of Beatrice Shilling's $8 carburetor restrictor that Rolls-Royce engineers called impossible. From a simple brass disc with a precisely drilled hole to a modification that protected over 10,000 RAF fighters and enabled 801,200 additional combat victories, Shilling's solution proved that brilliant engineering doesn't require complexity. Approximately 14,000 restrictors were produced between 1941 and 1945, installed in Spitfires, Hurricanes, and Seafires operating across every theater of World War II. Total program cost, roughly £8,000. Rolls-Royce's proposed alternative, £300,000 and 6 months of development. The restrictor was in operational service within 3 months of first testing, solving a problem that had cost Fighter Command tactical advantage for over a year. Beatrice Shilling's legacy extends beyond the restrictor itself. She proved that practical solutions beat theoretical perfection when time matters. She demonstrated that the best engineering serves operational needs first and technical elegance second. She showed that gender had nothing to do with engineering capability, a lesson that unfortunately needed proving in 1941 and still resonates today. The restrictor remained classified until 1949, but RAF pilots knew its value from the moment it entered service in March 1941. Miss Shilling's orifice saved lives, enabled victories, and eliminated a vulnerability that had plagued Britain's premier fighter aircraft. Not bad for a piece of brass with a hole in it. What impressed you most about this story? The elegant simplicity of the solution, the institutional resistance Shilling faced, or the measurable impact of such a simple modification? Let me know in the comments below. And if you want to see more stories about World War II's unsung technical innovations, the modifications, fixes, and solutions that changed outcomes without getting headlines, subscribe and hit that notification bell. Sometimes the most important innovations are the ones nobody notices. Thanks for watching WWII Aviation, and I'll see you in the next one.